In this video, I'll explain how you can find solution for knapsack problem by applying branch and bound design technique. The problem statement is like this. Given n items of known weights Wi and values Vi, I can take the values from 1 to n, and a sack of capacity W, you are required to find the most valuable subset of items that fit into the knapsack. That is, you have given n items. When you are filling the items into the sack, you have to take care that total weight of the items filled into the sack should not exceed the capacity of the sack, and value must be maximized. This is the problem statement. In order to do this, first, for all the items, find out the value to weight ratio and arrange this value to weight ratio in descending order. So, value to weight ratio must be arranged in descending order. This is the first condition in order to apply branch and bound design technique. Next is, you are required to construct state space tree to find the solution. Okay, so since it is a optimization problem and you are required to maximize the value, you are required to find out upper bound. So how to find out the upper bound here? UB equal to V plus W minus small w into Vi plus 1 divided by Wi plus 1. So this I'll explain with the problem. So this is the instance given to you. For this, you are required to find out the solution by applying branch and bound design technique. So look at here, already value to weight ratio is arranged in descending order, and you have given 4 items. For all the 4 items, so the value to weight ratio already found out, and it is being arranged in descending order. So first you are required to find out the upper bound. So in order to find out the upper bound, V, because in initial state you are not considering, that is in the root level, you are not considering any item into the state space tree. So there, when you have not considered any item into the sack, then the value earned is 0 and weight occupied into the sack is 0. So V is 0 here, plus capacity of the sack is 10 minus 0 into, since you are considering 0 item, so value to weight ratio you have to consider for V1 by W1. Okay, so if you are considering ith item into the sack, then value to weight ratio you have to consider for I plus 1. In this case, when you are calculating the upper bound considering 0 item, you have to consider value to weight ratio for 1. Okay, so V1 by W1 is 10. So 10 into 10, it's equal to 100. So this is the upper bound initially. That is, even if you want to find out the most valuable subset of items, the total value cannot exceed 100. This is the maximum upper bound possible for this instance of knapsack problem. Okay, so this is indicated in the root node. So once you have found the upper bound, now we'll see in the next iteration whether to consider item 1 into the sack or not to consider item 1 into the sack. For that, you are required to find out the upper bound here. So when you consider first item into the sack here, the weight occupied into the sack is 4 and the value is 40. So look at here. So weight of the first item is 4 and value is 40. Now calculate the upper bound. So V is 40 plus capacity of the sack is 10 minus 4. So total here is 76. And here when you don't consider V is 0 and W is also 0 and capacity of the sac is 10. So 0 plus 10 minus 0 into value to weight ratio is 6. So total upper bound here is 60. So when you look at this node and this node, this is the best possible upper bound. So consider this node with this you extend, that is considering the item 1 into the sac will lead to optimal solution. So that's why this branch is extended. So next you have to make a decision whether to consider 2 or not. When you are taking a decision here, when I consider the second item into the sac, already you have included the item 1 to the sac and the total weight is 4. 4 plus 7, that is 11. So 11 is exceeding the capacity of the sac because sac capacity given here is 10. And if you consider the second item into the sac, then the total weight will be 11, which is exceeding the capacity of the sac. So this is not feasible. Then we'll see without considering the second item. When you don't consider the second item into the sac, the weight whatever found in the last iteration, that remains same and value remains same because you have considered the first item. First item weight is 4 and value is 40, that remains the same. And now we'll calculate the upper bound. So upper bound equal to 40 plus 10 minus 4. 40 plus 10 minus 4. Value to weight ratio you have to consider for the third one, because you are in second iteration. When you are in second iteration, you have to consider third value to weight ratio. Third value to weight ratio is 5. So 40 plus 6 into 5, now the total equal to 70. So you don't have any option here because this is not feasible. You cannot continue the branch with this. So only option for you is you have to continue with this node. So when you continue with this node, now in the third level, you have to make decision whether to consider third item into the sac or not. So when you consider third item into the sac, the total weight is 9 plus 40 plus the value of the third item is 65. So total value is 65 and total weight is 9. So when you consider third item into the sac. Okay. And as usual, when you don't consider the third item into the sac, the total weight is 4 and value remains same whatever you had in the previous level. Now we'll see how to compute upper bound for this node. So upper bound equal to value is 65 plus W, capacity of the sac 10, minus total weight is 9, okay, into value to weight ratio. You have to consider this because you are in the third level. You have to consider fourth value to weight ratio, that is equal to 4. So upper bound equal to 69. And here in this case, V is 40 and 10 minus 4 is 6. 6 into value to weight ratio is 4. So 40 plus 24, that is 64 is the answer. Look at here. This is the best possible upper because you can get the most valuable subset of items filled into the sac. So consider this branch. So consider this node to branch. So now you have to make a decision whether to consider fourth item into the sack or not. If you consider fourth item into the sack, then the total weight will be 12. That is, already you have considered 2 items into the sack with the total weight was 9. And when you try to consider fourth item into the sack, 9 plus 3, that is 12. So which is exceeding the capacity of the sack, that is 10. So this is not feasible. Okay. Then next option we'll see here. The next option is not considering fourth item into the sack. So with that, weight is 9 itself and value is 65. So this itself is the optimal value. Why? Because we don't have any more items to consider. So with that, you can stop the iteration or stop constructing the state space tree. So if there are 4 items to be considered, then you will have 4 levels in the state space tree. If there are 10 items to be considered, then 10 levels excluding the root initial level. That is, I'm calling this as the 0th level. So if there are 10 items to be considered into the sack, then 10 levels will be there in the state space tree. So with that, what you can conclude is the optimal solution is when you consider item 1 and item 3 into the sack, the optimal value will be 65. So how did you get that? So start from the root to this node. So from root, how look at the path from root to this node is you have considered the first item into the sack, then not considered the second item into the sack, then third item is considered and fourth item is not considered. So 1 0 1 0. So solution vector is 1 0 1 0. This indicates item 1 is considered and 2 is not considered and 3 is considered and 4 is not considered. So with that, what is the optimal value you are going to get is 65. That's why it is called 0-1 knapsack problem. That is discrete knapsack problem. Why? Because we are considering either the full item into the sack, or if not, we are not, even though here space is left out here. So you can accommodate item with weight 1, but we are not considering fractional item into the sack. That's why it is called 0-1 knapsack problem, and the optimal solution here is 1 0 1 0 1 0. So this is how you can construct the state space tree in order to find out the optimal solution for the given instance of knapsack problem.